This is the Horten Ho-29 jet fighter bomber. It was intended to be one of Germany's superweapons in an attempt to turn the tide of the war with a fighter bomber that could reach a speed of 620 miles an hour. With its futuristic appearance and wooden framework, the Horten was unlike any other plane from World War II. But was it a real technological breakthrough for its time? And was it stealth? We've modeled the Horten in minute detail, inside and out, to try and answer these questions. The Horten Ho-29 was developed in the late stages of World War II and was the first flying wing aircraft, powered by jet engines. There were two flying prototypes built. In this video, we'll focus on the V3 prototype. That was captured by the U.S. Army in April 1945 and researched afterwards. Despite its futuristic shape, the airframe was quite rudimentary and extensively used wood in its construction. The aircraft was 9 feet 2 inches tall and 24 feet 6 inches long. The aircross wingspan was 55 feet 1 inch, and the wing area was an incredible 557 square feet. The formidable flying wing design was intended to increase speed and significantly reduce drag. The fuselage was built from steel and wood, and the two engines that powered the Horten Ho-29 V3 were incorporated into the plane's main body. The skin covering the steel airframe was made from plywood, which formed the recognizable aerodynamic shape of the jet. The aircraft's empty weight was just over 11,000 pounds, and its maximum weight was just under 20,000 pounds, which is about the same as a modern F-16, albeit without any weapons or fuel. The fuselage wings and landing gear were all built into a unified design. The aircross plywood skin varied in thickness to obtain an aerodynamic shape. The plywood was made of layers of thin veneer of European beech glued together, which formed a strong and lightweight design. It also had the advantage of using readily available materials. The plywood was attached to the metal airframe via wooden spacers. Since the Horten Ho-29 V3 was mainly made of wood, it could swiftly catch on fire if sparks were present. This is why the plywood skin was painted with a fire-repellent green paint. The Ho-29 was one of the first planes to use the flying wing concept, where the fuselage and wings formed a single structure. Why did the Germans choose this design, and what were its advantages? In short, it gave a greater lift and reduced drag, and gave better maneuverability. The plane's flying wing design was made from two delta-shaped dihedral wings, angled upwards at 4 degrees, relative to the aircraft's horizontal axis. The dihedral wings gave the advantage of better aircraft stability during rolls. A secondary spar provided attachment points for the elevator, a control surface specific to the flying wing design. The exterior of the wings was made of plywood boards. The almost tailless design of the aircraft did not include a vertical stabilizer, which increased the chances of side-slipping and, potentially, flat spins. The flying wing design without a vertical stabilizer wasn't used for over 50 years after the war in an operational aircraft. In part, this was due to the number and complexity of control surfaces that were needed to keep the plane stable. Ailerons were positioned on the trailing edge, towards the wingtips. They were used to control both pitch and roll, instead of the more traditional setup of an elevator. When both ailerons were in an upward position, the nose would pitch up, and when both ailerons were in a downward position, the nose would pitch down. When the aileron on the right wing was up and the left was down, the plane would roll to the right and vice versa. Each wing of the Horten had 2 flaps, On the trailing edge, these flaps were used during takeoff and landing, and in other situations, whenever the pilot needed to increase drag. Spoilers were another essential feature on the Horten. These were placed near the wingtips to create more drag and decreased lift. A lifted spoiler disrupted the airflow above and below the aircraft, increasing the drag. Other spoilers were placed underneath the plane. To the rear, spoilers were critical in maintaining stability during landing and also at high speeds. Next to the spoiler on the wing was a drag rudder. Drag rudders operated in pairs on the wing's upper and lower surfaces. When a drag rudder on one wing was used, it acted as a surface for yaw axis control. When the drag rudders weren't being used, they were laid flat. With spoilers and drag rudders activated at the same time on both wings, drag was significantly increased. While ahead of its time, the many control surfaces and lack of computer control made the plane exceptionally difficult to fly, a problem that wouldn't be solved for many years after the war had ended. The Horten was powered by two Junkers 004 B2 Jumo engines, each with a thrust of 8.5 kN, or 2,000 pound force at 8,700 RPM. The engine's length was 12 feet 8 inches. With a diameter of 2 feet 8 inches, the engine weight was 1,585 pounds. Air was drawn into the open front section, then compressed by an 8-stage axial compressor, and fed into one of 6 combustion chambers. In these chambers, the compressed air mixed with the injected fuel, and when ignited, it created a hot gas stream. 2 engines could propel the plane to a speed of 607 miles an hour. This came close to hitting the Luftwaffe's design target of 620 miles an hour. But the aircraft's rapid pace came with a price. The engines were exceptionally fuel-hungry. The high-speed performance of the engines led the turbine to be prone to overheating. By the end of the war, Germany couldn't source high-quality alloys. This forced them to utilize lower-quality steel in the engine turbines, reducing the engine service life to approximately 20 hours of usage. The intake cowlings were made of metal panels and hammered to fit over the plywood material on the leading edge of the jet. The exhaust panels were made from flat steel parts with a concave area. Metal panels protected the wooden structure of the plane. The fuel system consisted of 8 aluminum tanks, 4 on each wing. 2 smaller tanks were positioned on the wing's leading edge, and 2 more prominent ones on the central part of the wing. Their total capacity was nearly 528 gallons. And fuel consumption was around 343 gallons per hour. The fuel primarily used in the Junker's 004B engine was J2. This was a German World War II synthetic fuel. Made from brown coal, it was pumped using the electric pump, positioned next to the wing roots and the fuel tanks. The plane was designed to be armed with either 2 Mk103 or Mk108s. Both were 30mm caliber cannons and manufactured by Rheinmetall-Borsig. The Mk103 had a rate of fire of 380 rounds of high explosive projectiles and 420 armor-piercing rounds per minute. The Mk108 packed a significant punch and was most likely to have been used against bombers. Unfortunately, we don't have any precise information on how much ammunition could have been stored, but when compared to a similar system on the 262, it was most likely to have been around 200 rounds for 2 cannons, in which case the ammunition would have been fed to the guns from about. Also, the Horten was designed to take 2 1,100-pound bombs, albeit at the cost of increasing its overall weight, leading to changes in drag and required power. Even though armament was in the design, the prototype that was captured and inspected by the Americans was unarmed, possibly because of war shortages or because it was in an incomplete stage of construction. The Horten was a single-seat aircraft. The canopy was of a curved design, and the canopy's curvature significantly increased the pilot's visibility, and without vertical stabilizers, gave the pilot a clear view of the rear of the plane. The canopy consisted of two parts, with the windscreen at the front and a rear section, which slid back in order for the pilot to gain access. Directly in front of the pilot was a main panel, upon which were switches for ignition, indicators for vertical speed, turn, and bank indicators, airspeed indicator, and fuel warning lights. The second row of the panel housed indicators showing the flap's position, and a compass and two fuel indicators, one for the fuel tanks on the left wing and one for the fuel tanks on the right. There was also a direction finder indicator, which was an advanced piece of navigation equipment for the time, which picked up the direction of a radio beacon. Additionally, there were indicators for ambient temperature, engine RPM, and oxygen indicators showing pressure and flow. On each side of the control panel were two gauges for fuel injection, pressure, and exhaust temperature for each of the two engines. In the upper left corner were indicators for the position of the nose gear and the side gears. Fuel tank switches were on the left of the pilot seat, as well as a lever for deploying the brake, parachute upon landing, and a lever for controlling the spoilers. A flaps, retraction lever, and throttles were near at hand. On the side console, at the feet of the pilot were rudder, pedals, and toe brakes. On the right side of the pilot's seat was a circuit breaker panel, a control panel for communications, and a canopy emergency handle. Also on the right was a lever for the ejection seat. Using the manuals of similar German systems from the time, the following startup procedure would apply. The pilot would turn the battery switch to the on position. The inverter would be switched on, as well as the generators. He would check the throttles were at minimum. He would then start priming the engine by pushing the priming button and simultaneously activating the tachometer when the engines reached around 800 revolutions per minute. The pilot would activate the ignition switches once the engines reached around 1,800 RPM. The pilot released the priming button and activated the fuel selector switches. From then on, the fuel tanks would supply the engine. The pilot would push the throttle slowly. Before taxiing, he would lower the flaps. As the plane moved forward, the pilot would use toe brakes to steer the aircraft. Before takeoff, the pilot would hold the brakes and push the throttles to maximum. After releasing the brakes, the aircraft would start down the runway. When the speed reached around 93 miles an hour, the pilot would pull the stick back and the elevons on the wing would go into an upward position and the plane would lift into the air. The pilot would brake the wheels to stop them spinning, and then retract the landing gear. When the landing gear was fully retracted, hydraulically operated inner doors completely covered the wheels and gear, resulting in a very sleek aerodynamic profile. The flying wing design made the wing load smaller than similar aircraft designs of the time, increasing lift and reducing stall speed. The plane was intended to take off from shorter runways, which was a significant advantage during the war. Due to Allied bombings of the German bases, it was estimated that the Horten V3 needed a runway of only around 3,600 feet to take off. The aircraft was estimated to achieve a cruise speed of 392.7 miles an hour. The estimated maximum speed of 607 miles an hour would make it faster than the American P-51D and the British Spitfire. If the Horten Ho 229 had in fact entered active service, it would have proved to be a tough challenge for the Allies. The Horten was designed to withstand a force of 7 Gs. In a turn or a dive, however, research on the Horten estimated that the actual G-force it could withstand was 12.6 Gs at that level. It would have almost been certainly fatal for the pilot. The Horten's landing speed was projected to be around 97 miles an hour, so that the plane was able to land on the same short runway it took off from. The plane was equipped with a drogue parachute that opened during landing to quickly lower the speed. The futuristic shape of the Horten started a number of rumors, and in particular the question was raised: was it stealth? The aircraft's lack of sharp angles and sleek surface were thought to have decreased the radar signature. For decades after the war, Reimer Horten said he had also intended to add a charcoal surface to the Ho 292, further increase its stealth capabilities. In 2008, National Geographic recreated the Horten in collaboration with the Northrop Grumman Corporation to test its radar signature. Soon after the documentary was made, Northrop Grumman published a research paper stating that the design was somewhat lacking in terms of stealth and that it could not be considered a stealth plane, using the modern definition of the word. Although the plane wasn't as stealthy as many have thought, its high maneuverability speed and unusual aerodynamic shape made a unique example of military modernization. For its technical solutions and projected specifications, it is considered that this jet fighter was well ahead of its time. But the end of World War II also marked the end of the Horten's development. Despite 2 successful flight tests, on the second prototype, the jet never saw combat. The first successful operational combat-ready aircraft without vertical stabilizers was the B-2 bomber, which was introduced over 5 decades later. The Horten H-029 V3 prototype is currently preserved at the Smithsonian Air and Space Museum. This is the V-2, the world's first long-range guided ballistic missile. Faster than 4 times the speed of sound, it even traveled to the edges of space before descending to its target, and it was the first man-made object to leave the atmosphere, reaching a height of 128 miles above the Earth. The V-2 was a revolutionary weapon, unlike anything the world had seen before. In this video, we'll break it down in detail and explore whether it really had the potential to change the course of the war. In this film, we'll show the basic combat model of the V-2 rocket. My name is David Webb, and this is Blue Paw Print. The V-2 was a single-stage, liquid propellant rocket with a complex guidance system. It was 45 feet, 11 inches long with a fuselage diameter of 5 feet, 5 inches. Its wingspan was 11 feet 8 inches. The fuselage was built using thin sheet steel, wrapped around a solid framework of steel. Fuselage components were connected to the steel framework by welds and rivets. Fully fueled, the V-2 weighed 27,557 pounds. The V-2 missile was composed from 4 main sections: the warhead, the equipment section, the center section, and the tail section. The warhead section was mounted at the rocket's tip, complete with its explosive charge and fuses. 3 fuses were fitted into the warhead. A contact and inertial fuse were mounted right under the nose cap, and a second inertial fuse was mounted at the base of the charge. Any single fuse could activate the explosive charge. The warhead was loaded with 2,000 pounds of amatol, a highly explosive material commonly used during World War II. Amatol consisted of 60% TNT and 40% ammonium nitrate. Amatol was less powerful, but cheaper and more heat-tolerant than pure TNT. The equipment section housed the guidance and control systems. Inside this section were two electrically powered gyroscopes, which enabled autonomous control during flight. The horizontal gyroscope detected deviations in the rocket's pitch, while the vertical monitored yaw and roll. An analog computer connected to gyros and control surfaces, batteries to power the gyroscope's computer and other systems, and a main electric distribution board, which could receive external electrical power before takeoff. In addition to the instruments and the batteries, the equipment section housed compressed air bottles to maintain pressure in the fuel tank, located in the central section below. The largest section was the center of the rocket, inside which there were two aluminum-magnesium alloy tanks. The larger of the two tanks held fuel, while the smaller one was filled with supercooled liquid oxygen. Both tanks were insulated with layers of glass wool that was pressed with wooden chocks to keep the insulation in place under heavy acceleration. The bottommost section was the tail, which contained the rocket engine, the adjoining turbopump assembly and plumbing, as well as an exhaust thrust nozzle for large stabilizing fins or wings protruded from the tail section. Each was equipped with a set of external and internal control vanes for controlling the rocket. These would be controlled by the analog computer. The details of the V-2's launch and flight sequence will be covered later in this film. The V-2 needed to have a powerful engine to deliver its 2,200-pound warhead up to 200 miles distance. It was powerful enough to produce 55,000 pounds of thrust for more than a minute. However, for this to be achieved, the engine had to consume a lot of fuel. At very high pressure, German engineers designed an improved combustion chamber and pressure pump to meet these challenges. The combustion chamber was the core of the engine. The chamber had a double-walled structure, with both inner and outer walls made of pressed steel. Fuel lines were fed through the double wall to the injector head. The fuel absorbed heat from the chamber walls. This helped cool the walls of the combustion chamber, while also heating up the fuel. The injector head, consisting of 18 burner cups, fed fuel and liquid oxygen into the combustion chamber. The burner cups were also referred to as diffuser cups and were arranged in concentric circles. Each cup had a central liquid oxygen injector, surrounded by 5 rows of fuel injectors and feed holes connected to the chamber's double wall. The fuel evaporating from the cup walls gave them some protection against high temperatures. As well, 4 rows of feed holes were drilled into the combustion chamber to give further protection from hot gases. If too much fuel was pumped into the space between the double wall design, the pressure could lead to a catastrophic explosion. To counter this, a valve would release high pressure between the walls before it could reach dangerous levels. The supply of fuel under high pressure was provided by a special turbopump. The turbopump was in essence a steam turbine that drew fuel and liquid oxygen from the tanks and fed them into the chamber through separate valves. The liquid oxygen valve was connected directly to the burner cups via 18 pipes. The fuel valve directed the fuel through 2 large pipes, which split into 6 smaller subpipes. Before connecting into the inlet manifold at the bottom of the chamber's double wall, steam produced from a steam generator powered the turbopump. The steam generator, its fuel tank, and the turbopump were all mounted to a frame attached to the combustion chamber via 4 large bolt joints. The V-2's rocket engine was fueled by a combination of alcohol and water, with liquid oxygen serving as the oxidizer that enabled the fuel to burn. The primary fuel, labeled B-stuff, or B-stuff in English, was usually a mixture of 75% ethanol and 25% water. The fuel tank had a capacity of 8,179 pounds. Below the B-stuff tank was the A-stuff tank, a 10,802-pound tank of liquid oxygen. The liquid oxygen tank still needed to be continuously topped off right until the launch, as it evaporated very quickly. The rocket also carried 385 pounds of T-stuff, a mixture of 80% hydrogen peroxide and 20% water, and 48 pounds of Z-stuff, a mixture of 33% sodium permanganate and 66% water. T-stuff, in combination with Z-stuff, decomposed into oxygen and steam to drive the 580 horsepower turbopump. Finally, P-stuff, a label used for both compressed air and nitrogen, was used to fill special tanks throughout the rocket assembly to service various components and maintain pressure inside the fuel tank. The fuel was loaded into the rocket only after it was positioned at the launch site. V-2 missiles were stored in protected bunkers, empty and without the warhead mounted. They were transported to their launch points using a special trailer called the Mylar wagon. The Mylar wagon was usually towed to the launch site by 100 horsepower wheeled tractor, the Hanomag SS-100. The Mylar wagon was an ingenious design that could move the rocket to the launch position and elevate it to set the V-2 upon the launch table. Once the Mylar wagon brought the V-2 to the launch site, it was placed on the firing table or aviation platform. Although the V-2 could be launched from a permanent platform, it was mostly operated from the firing table. This was a robust, portable structure from which the V-2 could be launched to the skies. Constructed from welded steel and weighing 3,600 pounds, the firing table had the necessary strength to support a fully fueled V-2 rocket. The table consisted of 4 adjustable legs that allowed it to be leveled on uneven surfaces. On top of the legs was the support tube with a turning ring and rocket support pads that could hold the V-2 upright. Under the turning ring, at the central section of the firing table, was a pyramid-like structure called the blast plate, or blast deflector. Equipped with a hardened steel tip, the blast deflector was sturdy enough to withstand the intense heat and force generated by the rocket. Thanks to its shape, the blaster flexor dispersed the exhaust gases laterally, ensuring that there would be no gas buildups that could threaten the V-2's balance during takeoff. Once the rocket was precisely mounted, it would be released from the lifting frame's clamps and turned to 90 degrees left. With the help of a turning ring, the Mylar wagon could then be moved in small adjustments. With the lifting frame still raised, the crew opened the retractable platforms used to prepare the rocket for launch. Pinpointing targets 200 miles away was a formidable challenge that V-2 engineers tried to overcome. V-2 launch crews had to rely on specially prepared maps and precise triangulation of the launch position. Next, the V-2 needed to be fueled. But before the tanks were filled, the crew performed a dry purge of the tanks with compressed nitrogen to ensure that there were no leaks. First, the fuel tank was filled, followed by the liquid oxygen, and then the remaining tanks, 2 for the steam generator and several small nitrogen tanks. While still resting on the firing table, external electrical power would be supplied to the V-2. After fueling, the ground crew checked again that the V-2 was perfectly vertical and properly oriented. Finally, the hatches would be closed, the lifting frame lowered, and the Mylar wagon moved away from the site. The firing crew then connected the electrical igniter to the combustion chamber and signaled that the rocket was ready to launch. The troop commander would order everyone to clear the site before he entered the command vehicle, where he would give the order to begin the launching procedure. Inside the rocket, everything was set. The pressurized nitrogen forced the hydrogen peroxide and sodium permanganate into a steam generator, causing the two mixtures to react and produce high-pressure steam. That steam powered the turbine inside the turbopump to spin at 3,800 RPM each second. The turbine pumped 158 pounds of liquid oxygen at a pressure of 17.5 bars into the combustion chamber. It also pumped 127 pounds of fuel at a pressure of 23 bars. Inside, the mixture was ignited and brought to a temperature of 4,532 degrees Fahrenheit at a pressure of 15 bars. The ignition sequence did not produce enough power to launch the rocket. It only served to give the control officer an indication that the engine was working properly. If everything was in order, a switch was activated for the turbopump to increase its speed to 5,000 RPM, causing the engine to produce a thrust of 55,000 pounds. The electrical cables would disconnect electromagnetically, and the rocket would lift from the ground. The amount of fuel and liquid oxygen in the rocket's tanks allowed the engine to burn for no more than 70 seconds. At maximum power, it produced a thrust of 64,000 pounds, resulting in a staggering speed of 3,580 miles an hour, just under 5 times the speed of sound. During the ascent phase, the rocket was steered by 4 external air vanes and 4 internal jet rudders. The external vanes were conventional vanes connected to the fins, while the internal rudders were placed in the exhaust gases. Because of the intense heat produced by the exhaust, these rudders were made from graphite. After liftoff from the pad, the V2 would travel vertically until it gained enough speed for the air rudders to work effectively in tandem with the jet rudders. After 5 seconds of vertical flight, the mechanical motor would tilt the gyro that controlled vertical pitch. This signaled to the rocket rider to slowly pitch the rocket's nose downward. After 25 seconds in flight, the V2 would break the sound barrier and go supersonic. At 54 seconds in flight, the missile would be 49 degrees from vertical. At this point, the V2 has enough speed for the air rudders to be effective without using the jet vanes. Another gyro controlled and kept the rocket on course by using graphite jet rudders first, and then jet rudders and air rudders. If during flight, the gyroscopes detected any deviation in pitch, yaw, or roll, they could send an electrical signal to the analog computer known as the MISH, or mixing device. The MISHCAT would then calculate the necessary corrections to keep the rocket on its projected trajectory and send computed adjustments to the external air vanes on the stabilizer fins and the jet rudders in the thrust's airflow. To follow the predicted trajectory, it was crucial for the rocket to cut its engine at the designated moment. The device controlling the cutoff was called the integrating gyroscopic Once the rocket reached a predetermined velocity corresponding to the desired range, the PGA generated a signal to start the engine cutoff procedure. Once the engine had cut off, the rocket acted similarly to a regular artillery shell. It flew along its ballistic trajectory with just the air vanes keeping it on course. At this point, the rocket's angle of elevation was approximately 245 degrees. Even though the guidance system was sophisticated, for the time, the V2 was not a precise missile. At maximum range, the deviation between the target and impact was between 4 and 11 miles. Because of this, the V2 was suitable only against large populated areas, such as the City of London. From September 1944, these rockets started landing on London. The impact of the V2 missile was a horrific experience. It seemed to strike from out of nowhere. The first thing to be heard was a devastating explosion, followed by a huge cloud of debris. The roaring sound of the incoming rocket arrived only after the blast. The violent tremor caused by the explosion could be found from nearly half a mile away. After the war ended, American British and Soviet engineers showed particular interest in the V-2 development program. This interest was driven by the fact that the V-2 introduced several key innovations in rocket engineering, specifically in the design of the rocket engine. While the V-2 missile was a revolutionary design, it was not as effective as the Nazi leadership had hoped, and it was not the wonder weapon that could change the tide of the war. It was too expensive to be efficient, with the average price of a single V-2 missile slightly over $1 million in today's money, which was 20 times more than the cost of the V-1. If the V-2 had been introduced 2 years prior, before the Allies had landed in France, the Germans could have used it against British ports to slow down the invasion preparations. Being operational only in the autumn of 19, it was simply too late. Despite its drawbacks, the legacy of the V-2 was immense. The technical solutions introduced were applied in rocket design for decades to come. Sergei, the key Soviet rocket engineer and spacecraft designer, used many elements of German rocket designs for his own research that ultimately resulted in sending the first artificial Earth satellite, Sputnik, into space. On the other side of the Iron Curtain, Wernher von Braun, one of the fathers of the V-2, became a leading figure in the American space program. If it wasn't for him, the moon landing in 1969 might not have been possible. This is the Me-16-3 Komet, the only rocket-powered fighter ever built in large numbers and used in real combat. In 1941, an early version of this plane was the first to hit 1,000 kilometers an hour in level flight. It was built for one job, short missions, to attack incoming Allied bombers just before they could reach their target. We've recreated the Me-16-3 in detail to see how the German engineers designed this extraordinary interceptor. In this film, we'll be looking at the Me-16-3B1, a production version that fought from 1944 to 1945. We'll be showing it with the radiant red coating from the earlier test planes. My name is David Webb, and this is Blue Paw Print. The Me-16-3 was small for such an advanced aircraft, at just 8 feet 3 inches tall and 19 feet 5 inches long, only about half the length of a modern school bus. The aircraft's wingspan was 30 feet 6 inches. The fuselage was built primarily from duralumin and steel. Its construction followed a semi-monocoque principle, with formers and stringers carrying most of the structural load. Bulkheads separated the nose section, cabin fuel tank, engine and tail section. Each section was bolted to the bulkheads. The skin covering the airframe was also made from duralumin alloy, with the tail covered in steel riveted to the structure. This gave the aircraft its compact and highly aerodynamic bat-like shape. The aircraft's empty weight was 4,200 pounds. And it could take off at weights over twice that, up to 9,500 pounds when fully loaded. The fuselage of the plane was built in several parts, which were easy to assemble and disassemble, with many access panels to make it simple to perform maintenance and repair. The engine was mounted onto one compact unit, fixed to the rear bulkhead of the fuel tank section of the plane. The tail housed the rocket motor's nozzle and the tail wheel assembly. The vertical fin was mounted above this rear section. Because of the plane's small size, the onboard batteries had limited capacity, so the Germans added a small wind generator to the nose of the fuselage, which was powered by the small propeller-looking device at the front of the plane. This produced electricity for the radio, instruments, and weapons while the plane was in flight. The wings were where the Me-16-3's advanced design really stood out. They were relatively thick, about 15.4 inches at the widest section, and swept back at a 25-degree angle. This sweep angle turned out to be optimal for subsonic speeds, giving the plane exceptional stability and control. This design also made it a highly effective glider. The main wing structure was made from plywood, with 2 plywood spars in each wing. a forward box spar and a rear single spar. The wing outline was plywood as well, with the inner framework built from laminated wood. Strong glued clamps held everything together. The wing surface was also plywood, covered with doped fabric. A static wing slot, known as the slot, was located right behind the outer leading edge of each wing. This helped reduce the stall speed and made the plane more controllable at slow speeds, especially during landing approaches. Each wing had 2 fuel tanks, one 19-gallon tank in front of the main spar, and a 47-gallon tank behind the main spar. These held sea stuff, which we'll talk about later in this film. Each wing connected to a steel wing route fairing on the fuselage using 3 strong points, 2 on the main spar and 1 on the secondary spar. The fixings were made of steel and fitted with bolts. The wing root held the main weapons of the plane, 2 Mk-108, 30mm cannons. A protruding pitot tube on the wing measured airflow velocity to determine the speed of the aircraft. For transport by rail, the wings could be taken off completely and placed alongside the plane, allowing it to fit a standard railroad car on Germany's rail network. The test pilots were not pleased with the red color scheme of the earlier test units, which resembled the Red Baron. A little too much for the Mi-163B-1A. It was changed to the more traditional Luftwaffe camo patterns. The Mi-163's unconventional tail design required a different approach to flight control. Due to the extremely hot rocket exhaust, conventional stabilizers with elevators would have warped or even caught fire, so they were removed on the Mi-163 design. Instead, the main wings used surfaces that combine the functions of elevators and when both elevons were in an upward position, the nose would pitch up. And when both elevons were in a downward position, the nose would pitch down. When the elevon on the right wing was up and the left was down, the plane would roll to the right and vice versa. The elevons could move 12 degrees up and 16 degrees down when controlling pitch, or up to 11 degrees up and 14 and 2 degrees down when working as a. The vertical fin featured a rudder that could swing 35 degrees in either direction and controlled the yaw of the plane. The tail wheel was mechanically linked to the rudder. On the ground, the plane didn't taxi, but it was towed into position. The rudder pedals were just used to keep the plane on a straight path during takeoff. Large flaps were located under the wings, which were used only during landing. These could extend 45 degrees downwards. Trim flaps were placed between the fuselage and the elevons. The Mi-163 was built to destroy bombers. The 230mm Mk-108 made by Rheinmetall Borzig weighed 137 pounds each and were designed specifically for this job. The length of each gun was 3.48 feet and its barrel 1.9 feet. The pneumatic system cycled through each shot at 650 rounds a minute, with the muzzle velocity at 1,706 feet. With 60 rounds per gun, holding the trigger down would empty both weapons in less than 6 seconds. Each shell weighed 0.66 pounds and carried 0.18 pounds of explosive charge. They had very thin walls to maximize explosion. Normal 20mm guns often needed 20 hits or so to take down a heavy bomber. The Mi-163's cannons could destroy a B-17 with just 4 hits. A single direct hit was often enough to wipe out a fighter. Due to its distinctive pounding sound, Allied aircrews called the Mk-108 the pneumatic hammer. The guns usually were set to converge at around 500 to 550 yards. The defining feature of the Mi-163 was the Walter HWK-109 509A1 rocket engine. Weighing 375 pounds, it consisted of 2 main assemblies, connected by a cylindrical thrust tube. The forward assembly was roughly cube-shaped, It housed the turbine fuel pumps, control box, electric starter motor, and pressure-reducing valves. The rear assembly contained the combustion chamber, with 12 individual injector jets, arranged in 4 groups of 3. Starting the engine was a complicated process. Pressing the starter button kicked off a small steam generator. The steam spun a turbine, which powered the fuel pumps. After a few seconds, the turbine would reach its idle speed of around 25% of its maximum RPM. Before ignition, part of the steam was flushed through the combustion chamber and nozzle to clear out anything that might cause a misfire. The rest vented under the tail as visible white clouds. The throttle had 4 settings. At idle, no fuel entered the combustion chamber. The steam kept the pumps running at low pressure, and fuel valves stopped fuel from entering the combustion chamber. At minimum power, the steam flow to the chamber stopped. The turbine spun faster, pumps delivered fuel through the first set of regulator valves, and the first group of injectors would fire. This produced 247 pounds of thrust. Medium power activated the second valve set, and the second injector group. Maximum power engaged all valves and all 12 injectors, delivering 3,527 pounds of thrust. It was a complex system, and it only existed because aviation officials demanded variable thrust. In theory, the low setting was meant to save fuel at high altitude, but in practice, it barely helped. Even at reduced thrust, the engine burned fuel very quickly. At full power, it could only run for about 7.5 minutes. Just enough time to climb, attack, and try to make it back to base without power. For the fuel, the Mi-163 used T-stuff and C-stuff compounds. The T-stuff was a strong mix of hydrogen peroxide and water. It acted like the oxygen supply for the engine and a source of steam for the steam turbine. C-stuff was a mix of methanol and hydrazine and provided the fuel. The two components were which means that they ignited spontaneously when they came into contact with each other. The Mi-163 featured 3 stuff tanks with a total capacity of 306.5 gallons. 2 small, 16-gallon tanks sat next to the pilot in the cockpit, and a huge 275-gallon main tank was placed just behind the seat. Regular steel tanks were replaced with aluminium to prevent T-stuff from triggering corrosive reactions that could quickly weaken the metal. C-stuff was carried in for steel tanks, lined with enamel inside the wings. Altogether, they could hold 132 gallons. All of the tanks were cushioned with rubber bands to prevent friction and leaks. If a leak ever did occur, the T-stuff could dissolve organic tissue on contact. Small spills were life-threatening for pilots, and because of this, they wore heavy protective suits whenever they were inside the cabin. The Mi-163 was a single-seat aircraft. A North Point 6-inch conical nose plate protected the front, while bulletproof glass shielded the pilot from incoming fire. Additional armor plates protected the pilot's back, head, and shoulders. Directly in front of the pilot was the main instrument panel, arranged in 2 rows. The upper row housed the airspeed indicator, artificial horizon, and rate of climb indicator. The lower row contained the altimeter which measured turbopump RPM and a fuel gauge. The panel also included a clock and a compass for navigation, a thrust indicator, a temperature gauge, and a fuel pressure indicator for engine monitoring. Warning lights show the status of electrical systems, radio equipment, and oxygen supply. The standard Luftwaffe Revi 16B gun sight sat above the instrument panel. For aiming the cannons, behind the panel was a radio and battery system. The control stick and rudder pedals provided flight control, while the trim regulator allowed fine adjustments. Instead of a traditional throttle, a power setting selector was mounted over the left T-stuff tank. Levers for the landing skid and for jettisoning the canopy were positioned forward of the tank. On the right side, above the T-stuff tank, were controls for oxygen, electrical systems, and radio equipment. The Mi-163 had an unpressurized cockpit, which made it challenging to fly. Pilots required altitude chamber training and special low-fiber diets before flights to prevent internal gas from expanding painfully during the aircraft's rapid climb. To get the Mi-163 ready for takeoff, ground crew used the choice slipper, a specialized three-wheeled tug, to position the aircraft on its takeoff dolly. The plane never taxied under its own power because the rocket fuel was too precious. After refueling, the pilot began the startup sequence. He would turn the master switch to activate electrical systems, then the radio switch. The instrument panel came alive. It checked radio contact with flight control, then tested the control stick and rudder pedals. The pilot then moved the throttle to the start position. Only then could the starter button be pressed. Moving the throttle lever through its settings brought the engine to life. See stuff called double-wall combustion chamber. Then passed through atomizing nozzles. T-stuff then entered through its own nozzles. When the chemicals met, they exploded into flame, producing gases that provided thrust, starting the acceleration. German pilots used the Scharfer start, or the sharp takeoff. The Mi-163 accelerated down the runway on its wheeled dolly. At about 80 miles an hour, the control surfaces became effective. The pilot could finally steer with rudder and elevators, instead of just the tailwheel. At 200 miles an hour, the aircraft lifted off. It flew horizontal, building speed to 420 miles an hour, with the dolly still attached to the plane. Then the pilot would pull the skid up. Releasing the dolly's locking mechanism, a pneumatic ram pushed the dolly away from the skid. With the weight gone, the pilot would pitch the Mi-163 into a 70-degree climb, an angle no other fighter of the war could match. While most fighters of the war could manage a maximum vertical speed of 266 feet per second, the Mi-163 could rocket upward at 266 feet per second. In less than 4 minutes, it could reach 39,000 feet. And once it reached that height, the Mi-163 could cruise at 550 miles an hour. Fuel limitation was a major issue. Pilots usually only had enough for 2 attack runs before they had to break off and return to base. Most of the time, pilots spotted their targets once they reached altitude. Massive boxes of B-17s droning towards German cities. For the pilot, there was little time to make decisions. The concentrated burst of power from the rocket engine delivered altitude enclosure in a matter of seconds. Whatever happened next had to be completed. Inside that narrow window, the pilot had to choose: climb above the bomber formation, then dive down through the defensive fire, or make a low approach cut across from below, climb and dive again. Both methods reduced contact to a few seconds. The operational speed of 534 to 558 miles an hour created a huge aiming challenge. The pilots flew at slightly less than half the speed of their shells as they exited the gun. That forced the pilot to aim with a long lead, aiming not where the bomber was, but where it would be. The pilot fired short bursts, counting rounds and watching tracers arc towards the formation. High traverse speeds and rapid approach of the Mi-163 and efficient armor in the frontal projection made the defensive fire of Allied gunners almost ineffective. Once ammunition of fuel was spent, the pilot could return to base. Returning to base was the most dangerous time for the Mi-163. Without power, it became a glider, which was a much easier target for Allied fighters. Most of the Mi-163 shot down by the Allies happened during this gliding phase or after landing. During landing, the Mi-163 was lighter than at takeoff, had about half its starting weight, but it was slower and less able to turn. Approaching the runway, pilots slowed to below 185 miles an hour, lined up the plane, extended the landing skid, and lowered the flaps. The touchdown happened at around 140 miles an hour. The landing skid was less than perfect for absorbing shock, so extra springs were added to the pilot's seat to reduce the impact. The struts holding the skid were also rather weak. Any bump from a hole in the runway or a hard landing could break the skid and cause a serious crash. After landing the Mi-1, 6-3 was still vulnerable until ground crews could move it to safety. The Mi-1 6-3 was both advanced and flawed. It had groundbreaking technology, but also design compromises that made it hard to use effectively. The fact that it could fly as both a glider and a rocket fighter made it completely unique for its time. But even with the outstanding speed and climb performance, combat was limited by high speeds, short fuel time, and little chance for training. It was a remarkable but desperate design for desperate times. The Mi-1-3's combat record consisted of just 9 confirmed kills against 14 combat losses, plus additional pilot casualties from fuel accidents and crashes during landings. The Mi-260 was an iconic jet fighter from World War II. Designed by the Germans, it was the first mass-produced and deployed jet fighter. In this video, we'll talk about the Mi-262A1A Schwalbe variant. Translated into English, Schwalbe means swallow. As production of the Mi-262 was largely decentralized to avoid Allied bombs, small details or even instrument panel layouts can differ from plane to plane. That said, we've picked the details that we think are most representative of the aircraft. I'm David Webb, and this is Blue Paw Print. The Mi-262 was a low-wing, twin-engine monoplane. The length was 34 feet 9 inches or 10.6 meters. In cross-section, the main part of the Mi-262's fuselage looks like a slightly inflated triangle. With rounded corners, this shape was deemed to be the optimal for low cost, ease of assembly maintenance, as well as having low drag. The fuselage was built out of both steel and aluminum alloys. Some lighter alloys were harder to source during the war, and so steel was often used. For availability and cost reasons, this would come at the price of extra weight. Some non-stressed elements of the plane, such as the fuel tank cover and the control panel, were even built from plywood. The airframe consisted of longerons and stringers. Connected by the formers were made of U-shaped and J-shaped sheets of metal and were held in place by the length. Such a design could be made with the use of an unskilled and often unwilling labor force. The nose resembled that of piston-engine aircraft of the era. It had a small window at the tip for a camera lens, which we'll talk about later. There were main bulkheads between the ammunition, storage, and forward fuel tank. Another bulkhead sat between the forward fuel tank and the cockpit. One sat behind the cockpit and the rear fuel tank, and another was behind the rear fuel tank. There was an additional smaller bulkhead to separate the gun camera compartment. The bulkhead between the gun's ammunition and the forward fuel tank was understandably reinforced and fireproof. The rest of the bulkheads were aluminum, with stiffeners and open holes for cables, tubes, and linkages. The skin of the aircraft was 2 millimeters, or 1/16 of an inch thick. Sheets of duralumin plating. These were overlaid and riveted to the frame. Only the section housing the gun barrels had steel sheets to withstand the gun blasts. After assembly, the fuselage surface was polished and painted. Any holes or slits were covered with filler or doped fabric and then painted, reducing the drag of the plane. The wings were of a double spar design and were made entirely of metal. The main spar was made of steel, with an auxiliary spar made out of duralumin. Spars were connected by main ribs and auxiliary ribs. The skin consisted of 2 to 2.1 millimeter or 2/25 of an inch thick duralumin sheets. Only on the lower part of the wings, there were segments of 0.0 to 5 millimeter or 1/10 of an inch thick steel sheet. The wingspan was 41 feet 4 inches or 12.6 meters. The wings had an angle of sweep on the leading edge of -17 degrees. The transverse angle of a wing on a plane is the angle at which the wings are positioned relative to the horizontal axis of the aircraft. On the Mi-262, this was -5 degrees, which meant the wings were slightly pointed up. Along the entire leading edge of the wing, except for the areas occupied by the engine nacelle, were located retractable, automatic 3-section slotted wing slats. These slats were designed to improve the wing's performance at high angles of attack, such as during slow-speed flights or when maneuvering. On the trailing edge of the wing were flaps. When extended, the flaps increased the wing's surface area, generating more lift at lower speeds, thereby allowing the aircraft to take off and land at those lower airspeeds. To avoid pilot error on the Mi-262, the flaps could only be deployed when the undercarriage was lowered. The flaps were two-sectional and separated by the engine nacelle. Ailerons that controlled roll were also separated in two parts to avoid issues as a result of aerodynamic deformation of the wing. The tail consisted of a vertical stabilizer to which was attached a rudder to control the yaw of the airplane. There was a horizontal stabilizer to which were attached to elevators to control the pitch of the plane. Their construction was all metal. The tail assembly, like the wings, had a swept-back design. The horizontal stabilizer had a sweep angle of 23 degrees, and the vertical stabilizer had a sweep angle of 45 degrees. The landing gear was a 3-point tricycle scheme, with a front nose wheel and 2 main wheels under the wings, featuring oil pneumatic shock suspension. Usually the wheels were released and retracted by the hydraulic mechanism. The power was supplied by 2 jumbo 004B1 jet engines, each with a thrust of 8.83 kilonewtons, or 1,984 pound force. The Jumo 04 was the first successful axial compressor turbojet engine and a predecessor of all modern turbine jet engines. Air was sucked into the open front section, then compressed by an 8-stage compressor and injected into one of 6 combustion chambers, where the air mixed with injected fuel and was ignited, producing a stream of hot gas. Some of the power produced rotated an axial compressor. The remaining gases flowed through the nozzle and created thrust. The speed of the exhaust gas could be controlled by a movable inner cone called a zoibulb, or onion bulb because of its shape. The engine was 12 feet 8 inches long, or around 3.86 meters. It was 2 feet 8 inches in diameter, or about 81 centimeters, and weighed 1,585 pounds, or 719 kilograms. To fire it up, it was started by a two-cylinder, two-stroke gasoline-powered Riedel starter motor. The fuel used for the Jumo 004 was J2. This was a German World War II synthetic fuel. Produced from brown coal, the engine was designed to run on multiple fuels, including diesel. The two engines gave the Me-2-6 to a maximum level flight speed of 540 miles per hour, or 870 kilometers per hour. In a dive, though, it could potentially go much faster. However, the pilots were recommended to avoid a speed over 900 kilometers per hour, or 560 miles per hour. The Germans were the first pilots to encounter issues with flight approaching the speed of sound. During tests, a prototype plane exceeded 970 kilometers per hour, but had severe vibrations and temporary loss of control. There is a legend about an Mi-262 pilot who exceeded max speed and thus broke the sound barrier during World War II. But the airspeed indicator reading would have been inaccurate. At this speed, using a pitot tube for measurement, the rate of climb was an astounding 20 meters per second, or 67 feet per second. The rate of dive in operation was not that impressive. Compared to the late war Allied fighters, German pilots even slowed before diving upon American bomber formations so as not to exceed their safe speed during the attack. The fuel system consisted of two rubber, self-sealing main tanks of 238 gallons each, or 900 liters, as well as auxiliary tanks, which gave an additional 204 gallons, or 770 liters. The main tanks could feed either the right or left engine, and this was controlled by the pilot, using a switch on the left side panel of the cockpit. When the remaining fuel was reduced to 250 liters, or 66 gallons, a warning light was lit on the dashboard. The pilot had the job of balancing the fuel levels in the fuel tanks during flight to ensure stability. The maximum volume of fuel could, in theory, keep the Me-262 in the air for 60 to 90 minutes and give the plane a maximum range of 1,050 kilometers, or 650 miles. The main armament consisted of 4 Mk108 cannons with a 30mm or 1.2-inch caliber. Each cannon had a rate of fire of 650 rounds per minute, with a muzzle velocity of 520 meters per second, or 1,507 feet per second. The length of each gun was 3.3 feet, or 1 meter, and its barrel was 1.8 feet, or around half a meter. The electric triggers were located on the pilot's control stick. The cannon reloading mechanism was electro-pneumatic. Ammunition was stored in belts in protected boxes. A North .7 2-pound shell with 0.19 pounds of explosive was capable of bringing down a heavy bomber, such as a B-17 Flying Fortress or B-24 Liberator. In just 4 hits, it needed just a single shattering hit to bring down an Allied fighter. Due to its distinctive pounding sound and high rate of fire, Allied air crews called the Mk108 the pneumatic hammer. There were large spherical supports around the barrels, which enabled adjustments to the gun's convergence. The guns usually were set to converge at around 450 to 500 meters, or around 500 to 550 yards. In front of the guns was a gun camera that activated whenever the pilot fired any of his guns and stopped immediately upon releasing the trigger. Under the wings, there were mounted wooden racks with rockets. Several unguided missile models were tested and implemented on the most advanced of which was the R-4M 4-kilogram rocket. These missiles could be fired from distances of up to 1,000 meters or 11 yards. Their trajectory in the middle range was roughly similar to the trajectory of the shots from the Mk108, so the same gun sight could be used for the aiming of both weapons. Accuracy of these rockets was poor, so the Germans compensated this with numbers. Usually, an Me-262A1 carried 24 of these missiles in total, a dozen under each wing. The rockets had electrical ignition and could be launched as a volley or one by one. Aside from the fuel tanks and the bulkheads around them, the cockpit was protected by a frontal 3.5-inch 90mm bulletproof glass and a 15mm 3/5 of an inch steel backplate behind the pilot's seat. On later planes, the backplate was extended to reach behind the pilot's head. The cockpit had a 3-section canopy. The cabin's layout was traditional, with only the engine indicator panel taking more space than usual. Trim regulators, engine throttles, hydraulic, pneumatic, and oxygen indicators and controls were to the left of the pilot. Switchboard radio controls and read engine starters to the turbines were controlled on the right-hand side of the pilot. And the instrument panel with the 2 clusters of indicators, flight indicators to the left and engine indicators to the right, was directly in front of the pilot. A rocket launch panel was added below the main instrument panel. The gun sight used most of the time in the Me-262's short career was the standard sight of the Luftwaffe, the WWII-16B. This was a reflector gun sight, which projected a ring and crosshair reticle onto glass directly in front of the pilot. It was less effective than the later gyroscope-tuned EZ-4 to model, but was effective enough for short ranges and against large targets. To enter the cabin, a pilot would climb on the left wing and lift the middle section of the canopy and climb in. The seat had no padding, and so the pilot sat on his parachute. After entering, the pilot would buckle up. The pilot would activate a number of switches in order. The battery switch, then the inverter, then the generators. He would ensure that the fuel selector valve was off and the throttles were at minimum. He would push down the starter handle to prime the reel, starting motor. He would then pull the starter handle and hold, and at the same time he would press the tachometer button and hold it in. The engines would then rotate. When each engine reached 700 to 800 revolutions per minute, the pilot would press the ignition button on the right side of the throttle and hold. A deep throbbing noise would be heard as the unit began firing. Then the engine speed would be increased to around 1,800 to 2,000 RPM. The pilot could then release the starter handle and tachometer button and open a fuel selector valve. At this time, the rear fuel tank is supplying both engines. The pilot would slowly advance the throttle to 3,000 RPM. At 3,000 RPM, the pilot released the throttle ignition button, as the engine is now self-igniting. On the ground, the pilot steered by using the main wheel brakes. By now, the jets are running at 4,000 to 6,000 RPM. With the plane in position, the pilot would hold the aircraft with the main wheel brakes and open the throttles very slowly. For the engine to reach around 7,000 RPM, he would then switch the left engine to the front main fuel tank and the right engine to the rear main fuel tank. releasing the brakes and opening the throttles fully, would start the plane down the runway. All the while, he would make directional corrections with brakes only. The control stick would be in a neutral position after the takeoff speed of around 125 miles per hour was reached. The pilot would pull gently back on the stick. This would move the elevators at the rear into a raised position, and the plane would gently become airborne. To stop the wheels rotating, the pilot would apply the brakes before retracting the landing gear. Initially, the Mi-262 would climb higher than the expected target formation altitude. Once in position, the pilot would switch on the power for the guns and rockets and flip the metal safety cover forward on top of the control stick. Then, when the enemy was in sight, the pilot would quickly fly to the side and above the enemy. When ready, he would slightly bleed the speed, turning into the formation and dive. He would aim to cut across the box formation of the bombers. Looking through the WWII gun sight, the pilot would see the glowing with the range marks and the ring. The pilot calculated range and deflection based upon experience. If taking on a B-17, the pilot would look as to where the wing of the B-17 would appear on the sight. If the wings filled 2 full marks, that would mean the distance was around 11 yards, or 1 kilometer. When the plane was at a distance of 11 to 600 yards, or 1 kilometer to 550 meters, the pilot would press the switch to launch a volley of rockets. And then when the B-17's wingtips filled almost the entire circle, the distance would be around 330 yards or 300 meters. The pilot would press the buttons to fire short bursts from his 30mm guns to shoot at any available target as he passed. After diving, the Mi-262 would try to climb back higher than the bombers to make another pass. But if too many escort fighters were gunning on him, the pilot may simply accelerate and outrun the pursuers until they lost sight of the German jet. When low on fuel or ammunition, the pilot would head for home. Inability to maneuver and relatively slow speed at takeoff and landing was used by Allied pilots to catch the Mi-262s when they were at their most vulnerable. By diving at slow and unmaneuverable targets from above, this tactic got the nickname rat catching. It's estimated that around 1,470 Mi-262s were built in total. Due to delivery and logistics issues and a lack of trained pilots, only around 300 Mi-262s took part in action. Eventually, the Mi-262 proved to be a formidable interceptor, but at this time the German industry was too damaged, and the U.S. industry produced too many planes that the Mi-262 could not really make a difference. The Mi-262's conceptual scheme was copied in many designs, such as the Soviet Su-9 and the Japanese Nakajima Kika. Some design ideas from the Mi-262 were used in several prominent planes, including the MiG-15 and the F-86 and B-47s. The turbojet engine housed in an underwing nacelle proved to be such a successful design that it still features today in almost all modern airliners. Thank you for watching. If you spotted any errors, please let us know in the comments. We're looking to continuously improve. If you want to look inside more iconic World War II aircraft, then check out this video about these incredible planes.